Hello, everyone, and thank you for joining us for our presentation on MPC Research 595, and that is the design of mechanically spliced precast bridge columns. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which makes research like this possible, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. Our speaker is Dr. Mostafa Tazarov. He's an associate professor in the Department of Civil and Environmental Engineering at South Dakota State University. His research interests include the resiliency of civil infrastructure, advanced and sustainable materials, accelerated construction, large-scale testing, and computer vision in structural applications. With that, Mostafa, I will go ahead and mute myself and turn the presentation over to you.
Thank you so much for the nice introduction. As Chris mentioned, we will go over not one MPC project, but 2 MPC projects that we have been doing in the past 5 years. And we'll give you a juice of the studies and what we found on how to design columns when you want to use coupler in those. First, let me thank my colleague, Dr. Webby, and our student, Ted, Puskar, Evan, Cal, and Matt, that they helped us through the project in the past 4 or 5 years and helping us to reach the conclusion and the result that we will present today. So that's that. And I would also like to thank MPC, South Dakota State, and multiple industry partners that helped us throughout the project. And without their help, we really could not perform the study. So I actually appreciate their help and support. I will just give you a quick background of the ABC connections or accelerated bridge construction. And we will go over together on the behavior of coupler, what they are, how they behave, and when you put them in the column, how the column behavior will be changed. And very quickly toward the end, we will go over how or what tools you have now to design a column with coupler. So as you all know, a conventional column mainly is out there to meet these 4 bullets that I have here. They have to support the weight of the basic superstructure. They have to provide sufficient ductility and resiliency as a general term. And when they are located in a high seismic area of the nation, they have to dissipate energy. And by current code, we allow them to get some damage if they're in high seismic area, but they should not fail or they should not collapse. When we want to replace conventional columns with precast one, then all the rules that the precast or the conventional one should serve, the precast column should also meet all of those rules and actually requirements. And there are ways that would be above and beyond topic of today that you can also improve the precast column behavior and make them even better than the conventional. But again, we won't talk about those today. We will just touch base on precast columns and what tools we have for that. So there are a few proved tested connections out there that you may call suitable for seismic application. The first one, which is topic of today, is when you want to use bar coupler. You can use coupler within the column. You can use coupler outside of the column in cap beam footing, and we will talk about their effects today. Another way to connect a precast column to adjoining members through something called grouted duct. So what it is, you leave a duct 3, 4, 5 inch in diameter. 5 is big, but 4 inch in diameter usually. And then you have them as many as longitudinal bar you have in the adjoining member, and the column is built at the plant with those bars sticking out. So on the field, you just lower your members, fill the duct with the grout. So that's the grouted duct. The pocket, let's say, connection, they also called socket connection, is the same mentality, but rather than having multiple ducts, you have one big duct that will house the entire column. And then we will call that a pocket connection. And let's say another one, if you don't like moment, you want to kill your moment, there are new hinges out there that you might use, and it's called piping connection. So what it is a steel pipe in column, and then there's a steel cup or socket in the adjoining member. These guys just sit on top of each other, and a steel connection provides shear for you, and moment will be significantly reduced. So these are main general proof tested ABC connections that we have out there. We did a few years ago as part of an CHRP project, the survey of state DOTs, and we wanted to know if they are familiar with these ABC connections. We had 33 states participating in the survey, and what we found was they are most familiar with mechanical bar splices and the connection associated with it. And then the next one was the grouted duct connection, and pocket one was the last. And when you go through advanced materials, those guys are the last in the ranking by DOT folks. And we also asked them, hey, have you ever used any of these ABC connections in your state? And we found that 17 projects used mechanical bar splices in the column. In those 33 DOT that participated, 10 grouted duct and 8 pocket connection. This survey was, I guess, in 2017 or 16, so it's a few years old, and I'm sure that there are more numbers that we can basically compile and put in this study. But my point was, people or the engineers know couplers better than the others. And here are a few samples of field application. They have been used in Utah, Florida, and Colorado. And the main idea is your column is precast. You just leave some couplers. We'll talk about it in a moment. And then you lower the column, and the coupler will match the bar, and you fill it with the grout, and there are different types as well. So here are just a few examples that I found to share with you. So let's talk about couplers, what they are. So you all know that the most convenient way to splice bars are lap splicing. You put them side by side, you just tie wire them, and the concrete will take care of the rest. But there are a new way of connecting bars, which is more direct, more continuous, and is through, let's say, a mechanical device. Here is a picture of all those that we tested before. We tested more than 160 of those in past. And you can see that they are, if you pick the correct one, and we will talk about which one is the correct one, they should be able to rupture the bar consistently. So bar couplers are good, are reliable if you pick the correct one for your application, and they should be able to save some money, not much, save some money, because you're not overlapping bar, you're doing it or basically directly. But we need to do more study to find what is the cost benefit for that. But we are not doing it for connecting the bars. Now we want to use them to connect columns to adjoining member. So if we can do that, there will be 3 or 4 times faster construction. That would be your cost saving there. And here are a few examples of different couplers that are out there. In general, we have categorized them into 6 groups. One is in which that the bars are headed, and then you use 2 matching threaded couplers to connect them, or we call them headed couplers, and the heads bear against the coupler. Okay. Another one is you have a sleeve, the bars goes in halfway in from each side, and then you press the sleeve to the bar. We call switch coupler. The threaded one is obvious. You have threads on both sides, and the big nut will take care of the connection. Most field used coupler for a column so far has been the grouted couplers, because they give you more tolerance. They are larger, but they will give you more tolerance. Bar goes halfway in, you fill the sleeve with a high strength grout. And there's another one called shear screw. You have, again, bars coming from either side, and then you torque these screws, and they shear off at the desired strength, and then the coupler should be strong enough to hold the bar in place. And we have a combination of any of these couplers that you see on a screen, and we call them hybrid couplers. So that's a combination of at least two mechanisms that I just showed. There are a few that have used three mechanisms in that as well, but overall we will call them hybrid couplers. I'm just showing one sample per each. There are more than 60 couplers at least out there in the market, and new ones is coming, but overall you should be able to categorize them or put them in the 6th category here. Then the next question is, okay, we have couplers, 60 of those in the market produced by different manufacturers. Now I want to use for ABC connection of columns, how I should do that. So you have your products, different one. The first question is which one you should use. And the second question will be what are the effects when you want to put them in a precast band. We will address these two big questions today. And what we have found early on 5-6 years ago when we started the study was, let's see what are the gaps. The first one that we saw was there is no unified acceptance criteria and testing methods for couplers. There are one ASTM, Caltrans has its own, AASHTO has its own, but they are not meant to be used for precast, and they are not meant to be strong enough to rupture the bar. So we need to change those guys for a ductile member application. Then there was no model out there. How you want to model a coupler in your day-to-day design. Then there was no comprehensive test data. There were some isolated here and there, but non-unified. And then same story on the column side. On the column, there was no database of columns with coupler, some isolated studies, but not from a holistic approach or perspective. Then, and the last one is that there was no design method on columns. So in past 4 or 5 years, we have been studying, and thanks to MPC and other sponsors, and filling these gaps one by one. And now I should be able to give you answer in all of those 5 big gaps that we have. And we will discuss how we fill those. So 2 MPC projects, 1 NCHRP project, 2 other USDOT projects. We are putting all of those together for you today here, and we'll give you some basic useful tips for the daily design. So let me be short and brief and just tell you what would be the best acceptance criteria and material model that you can use, and then move on to the next or more interesting topic. So again, there are some criteria in AASHTO, in Caltrans, in ACI, saying type 1 coupler, type 2 coupler. They're all good, but they are not meant to be used in ductile members in high seismic region. So we ended up with this definition of acceptable or acceptance criteria for coupler. The first one is the length should not be more than 15 dB, and this dB is the bar diameter. This limit was based on test data we have. Now we should be able to a bit to stretch this to 17 or 18 dB because now we have data for it. And if you are using coupler in a bridge column, that coupler should be strong enough to consistently rupture the bar outside the coupler. We call the coupler region having a distance at the either side of the coupler. So you should use only the coupler that can fracture the bar. And the strength of the entire splice should not be less than 5% of your bar itself. So we are putting that because we don't want manufacturer play around or heat treat or do anything that will artificially rupture the bar but not be able to reach the strength limit. So we have both the strength and the strain limit by these two two twig requirement. So now on, I will refer to these couplers as seismic couplers. Again, there is no definition, AASHTO, Caltrans, or in the ACI. So the seismic term, seismic coupler is a new one, and those are the good ones that you can use in bridge design, beam design if they're in high seismic area of the nation. So the second one, again, I will be brief, but the model that we developed and has been proved over and over is reliable as this. You have a splice with coupler. You put them in tensile test machine. You test it to failure. We know that because of the anchoring mechanism, not the entire length of the splice will contribute to the total elongation. So is there any way that you can utilize that knowledge and make a model out of it? And that's what we did. We said, okay, let's assume a portion of the coupler is rigid, 5%, 10%, 20%, 100%. And let's adjust your stress strain diagram of original bar counting for coupler. So because of that rigid length factor, your spliced specimen will always have a shift in the stress strain diagram, and usually your strain is smaller than the reference bar. So that's your model, and with one simple equation, you should be able to model that strain or update those strain values at the critical point. And here's a validation. Again, we will talk about more, but we have done that for more than 150, 60 samples. And this model seems to be accurate enough to represent the coupler behavior. The black one is test, and the gray dashed line is the model that you see on the screen, and the dot one is the reference bar that goes to 10, 12% strain capacity, whatever it is. So that's your verified model. Then let's move on to the coupler behavior and standard testing of those guys. So that's the first MPC project we did. We contacted all manufacturers in the US and a few abroad, and we asked them, hey, are you willing to donate samples for us for testing for you? And then we found that out of 60 products, 10 of those are okay to be tested. We wanted to use those that could potentially rupture the bar, and here are those AASHTO and ACI types that we've been discussing early on. And we ended up with more than 160 couplers to be tested under either monotonic or cyclic loading. Here is our proposed test setup. If you want to use a bar, you all know 8-inch, 4-inch with some 5 dB. Difference between the grip is your typical non-spliced bar setup, but when you have coupler, we are proposing that you have to have at least 6 times the bar diameter as the clear distance between the grip and the outer face of the coupler. Leave 2 dB for measurement, and that would be your setup for a specimen with a splice. So we did that, and we tested all of those couplers. We also worked with Epsilon, and they made a new coupler or a strain extensometer for couplers that can accommodate different couplers, different sizes. We worked with them to adjust their, let's say, basic sensor, and now they should be able to accommodate up to, I think, up to 18, number 18 bars as well. So we did that, and we found it very easy, very reliable, very reliable device. Here is a video of one of the monotonic tests we did. So I hope that on Zoom you can see them nice and smooth. The top portion of the machine is going up, pulling the entire piece up with it. And I think there should be a rupture down there. I should be able to show it to you when it's done. Definitely the video is on actually fast or 32 times faster than what it should be. And we tested the couplers based on the STM standard and change the rate a bit for accommodating the coupler. So that was just one sample to show you, and we documented the strain and the forces and everything. And here is a sample for the cyclic test that we did. That was half cycle testing, only in tension. So the machine goes up, performs 4 cycles per strain level, then goes up to the next level and perform another 4. And we compiled, or we did all, we test all the specimens with that. Okay, again, the video is 32 times faster than what it should be. The bar ruptured down there, and we documented all of those data, and I'll present a short result here for you. So if your coupler is a seismic coupler, you should always see consistent results. For example, here I have a threaded coupler, and I see that always it was able to rupture the bar outside the coupler region. So that would be a good coupler for seismic application. Here is another one, bar ruptured outside. You can also take a look at the strengths, which is matching more or less the reference bar. So we post-processed all of those tests, put them in or perform a statistical analysis on those, and recommended a beta value or the rigid length factor for each of those. And here are a few samples of the cyclic tests as well. What we found is really you do not need to perform cyclic tests to understand the behavior of the coupler itself. Usually the monotonic test will be enough, will be strong enough to give you all the information you need for the design and also to validate it. But we're putting the language for cyclic and dynamic test just in case if the device has never been tested for cyclic analysis or want to be used in high seismic region of the nation. But overall, for design purpose, don't need it. And here is a summary of the statistical analysis that I basically mentioned earlier. For number 5, number 8, number 10 bars, we tested 3 to 5 samples, I think 5, and then we got the average of the beta value for you. So no one, if you want to use a grouted coupler, for example, by an MB, and you're working with number 10 bar, you come to this table, your beta factor is 0.85, and if there is a design method based on that, you should be able to move forward with it. If that's a new device, you should be able to test and obtain beta through the test and basically report it to your engineer. The way that we are thinking is this beta factor has to be performed by the manufacturer under in a certified lab, and they should need to report this beta factor in their brochure for the engineer to use. So that's our thinking, and that's what we propose to ASHTO. I'll talk about that later. Okay, here's this comparison of if you're using multiple different couplers and you want to see how their behavior changes compared with unspliced reference bar. Couplers consistently have a lower strain capacity compared to on a splice bar from 10% to 65%. So they can sometimes significantly reduce your strain. Strain reduction doesn't necessarily mean they are bad product. Usually threaded couplers have the most reduction in the strain, but their lengths are 1/4, 1/5, 1/6 of a grouted coupler, which has more strain in it. So there is a trade-off of the coupler length versus the rigidity, and we will talk about that. We talk about their effects on the column design, but it does not necessarily mean that's a bad coupler. As long as it can fracture a bar, it is a good coupler for seismic application, for column application. So long story short, we synthesized the first MPC result, and we developed a standard testing method for couplers, and we proposed those to ASHTO as a national document for testing couplers. And if you're interested to have the language and you have the test setup, I guess 14, 15 pages based on the STM language, they should be in the NCHRP report 935, or just shoot me an email. I'll be more than happy to share that document with you. So we propose it to AASHTO and ASTM as a standard testing method for couplers to be used in seismic region. So that's the first part of the study. Let's move on to the column. I'll try to be quick because these are very large studies and we just need to know the juice of it. Studies after studies, they were saying if you use coupler at the end of the column or in seismic, let's say region they call plastic hinge region, there should be a reduction in the displacement capacity of the column. So for example, the gray one is CIP and the other two here are those with couplers. Unless you do something with it, you would always get a smaller displacement capacity and you always get slightly higher force capacity as well, but it's not much. We will talk about that. And there are isolated studies like this one. I did one, my colleague did 4 at Utah. Dr. Pantelidis did 8 or 9, but we didn't study how multiple different couplers would affect columns behavior if you test them in a systematic way. And that's why we did the second MPC study and came up with 8 testing or 8 column testing. I will exclude the last one because it was not related to this presentation today, but we tested 1 conventional cast-in-place column and 6 precast column with different couplers, grouted, threaded, and de-threaded coupler. And there was a new one, grouted headed, produced by HRC for the first time, and we used it here for the first time, tested for the first time to see how they perform. And I'll talk about all of those here. You have generally few ways to connect precast column to adjoining member. Once if the column is, or the column is built with the coupler inside it, so then that would be one way. Sometimes because of the connection type, like if you're using threaded coupler, you have to have a void around the column. Your coupler should be exposed for assembly, then you have to do the closure pour. So these were the 2 types that we use. I think all of those but one with this detailing and one which is PTV, a threaded coupler, we use this detailing, and that one is the repairable one that I won't discuss today. The idea was, can you expose your bar through couplers and make them accessible after the earthquake and change them as many times as you want to make your column repairable. So that would be another topic, another presentation, most likely at MPC. The coupler types that we picked and the companies agreed to help us with those was Dayton, the grouted one, NMB, Splices, slip, the grouted one, Dextra, one side threaded, one side grouted, and Vent, one side threaded, one side grouted, fully threaded and Vent, and headed one side, grouted on the other side by the HRC. Here is the major distress strain diagram of all of these splices, one sample for you to see. The black one is the reference bar, and the others you can see that copper consistently reduce the strain capacity. For example, if the reference one was 10 or 12, some of those or most of those are 4 to 5% strain, and 1 or 2 are slightly higher. So that would be the effect of coupler on the strain capacity. Then we put those in half a scale column, 8 feet tall and 24-inch inside dimension. We used number 8 bars, 10 of those, and we followed the design of a high ductile column. We shoot for displacement ductility capacity of 7. So, or hoop spacing was 2 inches. We used number 4 as hoop. And then we tested all of those using the setup that you see. We had a concrete block back there, actuator pushing the column back and forth, and we had 2 rods and jacks to compress the column and apply the axial load to it. I think the axial load was 155 kips, and the actuator could push the column 15 inches back and forth, and we tested them slowly from very small amplitude to large amplitude displacement, 2 amplitude or 2 cycle per amplitude to represent the cyclic loads. The construction was very simple for us, at least, or not simple, but very easy. For the precast one for CIP, again, here's the detailing for it, and our graduate student did a great job, and they built the cage, they built the form, and they poured it. We did the footing first, and then we did the column second. That was not super hard for us. For a professional contractor, that's just everyday life, right? And for the precast one, we wanted to involve industry in the process, so we invited Gage to help us with the construction of all precast column, and they kindly agreed to do it. And the columns were built in Sioux Falls at Gage Brothers plant, and they shipped that to us. We quickly assembled them. My graduate student could do it in 30 minutes. And then when the column was basically secured, we used the hand pump if they needed the grouting, and pumped through the bottom vent and waited for the grout to come out for a few seconds, and then we capped the top and bottom one. So basically very easy construction technique. We did the footing in-house, but again, the precast columns were all built at Gage Brothers. Here is a video of the column testing, one sample for you to see how the testing was done. I think each column took us 4 to 8 hours to test, depending on what displacement they fail. Again, pushing the column back and forth and marking the cracks, and then at some point you will see spalling at the side of the column, and then more extensive bar will expose, and at some points bar will either rupture or pull out from the coupler base. A few cases we had that too. You can also see the sun moving fast. Again, this video has been processed to be, I guess, 64 times faster than what we tested. Just wanted to give you a sense how the testing was done. So that's summary of a few hours of testing in a minute. So that's how we perform our tests, and let's share some results with you. The conventional column cast in place, that is the damage at 2% drift ratio, and drift is the column lateral displacement to height of it. So I think 1% drift for us would be equivalent to 1 inch, if I'm not wrong, or something very close to it. So at 2% drift or 2 inches, typical fractal cracks for CIP. But if you take a look at the precast column, you may notice that the damage is not, or the cracking is not as extensive as the CIP. The main reason is some of those couplers are big, laterally stiff, will reduce the damage, apparently shifting it away from the coupler. Maybe at the failure point, you will see it better. So that's the CIP failure, bar rupture, buckling of the bar, and typical failure at 10% drift or 10 inches. And for the one with grouted coupler by Dextra, if you compare the two damages, you see that that one apparently has less damage. This is again because the couplers are big, stiff, and shifting the damage and nonlinearity away from it. And you can see a similar behavior everywhere. For PHT, you see on this screen, I'll talk about that later again, is you don't see that much damage because it failed early on. And what we found later was this coupler was supposed to be seismic. That's what the manufacturer told us and showed us the result, and they were right. But when they shipped this to us for unknown reason. Following all of the procedure, this coupler did not perform as a seismic coupler. Bar pulled out from it. As a result, when we used it in a column, bar pulled out from the coupler at the lowest displacement among all columns. So that one is a proof that we should never ever allow non-seismic couplers to be used in a column. But if you use seismic couplers, you should be able to achieve very large displacements. And here's a force deformation behavior. The black one is CIP. You always get fat, loop, stable forces everywhere, and that's great. And you can see that all of the precast column had higher forces than CIP, and they followed more or less the same behavior, except one column, which was the headed and grouted coupler. There was a small gap there between the head and the seating area. That minor gap caused some pinching here. I think that would be the blue curve here. But overall, very similar behavior to conventional. We're happy with the result. They are good to go, at least from this perspective only.
Dr. Cesar,
yes.
There was a question as far as the vertical load being applied to the column during testing, or was it just simply a displacement test only?
No, we had 155 kips as axial load on column.
Okay, thank you.
Sure. And here is a kind of backbone of all tests that we did in putting everything in one picture. Again, the black is CIP. We were able to have a displacement ductility capacity of 12, and you can see that for all other precast columns, that ductility was smaller. And this is because of the coupler effect. The other effect of the coupler is all of the precast columns had higher forces than the CIP, 10 to 15%, not much, but some. And that one is again because of the lateral strength or stiffness of the coupler when you put them in the column. And here is the PhD column, the one by Dextra. Again, that was not meant to be non-seismic. Just happened. We don't know why. Probably with better quality control measures, they should be able to improve the coupler behavior. But as it is, it's non-seismic coupler, and you see that it achieved the lowest displacement or drift among all columns. However, if you put this column in California, in downtown Los Angeles, the maximum drift that you expect or displacement that you expect to see under design level earthquake is 2.2 inches, 2.3 inches, while this column achieved 3.5 inches of displacement. So it still is okay, but it's not in the realm that you feel comfortable with. And then you have to change the coupler to a seismic coupler. Then let's say the next one is at 5. So you have 2 times or twice or 100% reserve capacity, you feel more comfortable, and going in the less, your reserve capacity will be higher, more comfortable in terms of higher safety factor for you if you want that. And if you take a look at the current AASHTO requirements, all 6 precast columns that we tested met all the AASHTO requirement. I'm talking about maximum demand at the site of, we are talking about downtown Los Angeles, minimum displacement capacity of 3. All of these columns met the requirement, so they are recommended for use in all 50 states. But again, PhD Dextra needs to improve the coupler behavior and make it seismic coupler. If they do, this number will bump up to 5-6%. That's our expectation of this product. So overall, okay, we're happy with the result. And let me share you the strain profile, and that's very, very interesting. I think the black one is again CIP, and the colored one, they are all the copper one. I had 6 of those, couldn't fit all those here. The bottom is top of the shortest coupler we have, and the top one is the top of the longest coupler we have. It's evident that wherever you have a coupler, your strain is smaller, and the coupler shift the nonlinearity, shift the yielding outside of the coupler region. For example, here, I think that would be a good example. In CIP, you have good strain penetration into the footing. 0 means column footing interface, while when you have couplers, they are usually higher than the CIP. Means that, again, couplers are shifting the yielding away from it. And you can consistently see the same behavior overall. So our message is coupler will shift the damage away from it and will cause change in the strain profile, and we have to be careful about that, how we use it. Okay, so these are, again, very short and brief findings that I shared with you. Now let's talk about how we should design a mechanically spliced column. On testing side, coupler testing, I said that we propose AASHTO or STM standard to basically AASHTO, so that was there. But for column, we have a few design methods. Utah has its own, Florida has its own. We proposed something in 2016, and then based on the study of the NCHRP work and this study, we propose a new design method to AASHTO, and we're hoping that that would be as part of AASHTO SGS for ABC column or ABC column connection. Here are the three methods that we propose to AASHTO for splice column. The first one is that you adjust your displacement ductility capacity. I'll talk about that. In the second one, you will adjust your plastic hinge lengths accounting for coupler. Again, I'll talk about that. And the last one is a pushover analysis and including the stress strain diagram of the coupler. The whole three were established around the idea that if you have a coupler, there is a change in strain and yielding distribution. Can you model that? Yes, using the shift in the stress strain diagram, you should be able to model that, and wherever you have coupler, you need to use this shifted stress strain diagram, and outside you can use your typical strain. So all three methods are based on this general observation that the strain within the plastic hinge lengths, wherever you have couplers, is smaller than a typical column. And let me go over each of those very quick and fast. In the ductility equation, we introduced the beta factor, how much of the length of the coupler is rigid. Has a range of 0 to 1, but 0.5 to 1 is a typical design value. For different coupler, the manufacturer should report that to you. And then where you are going to use it is right at the interface, or it's slightly shifted. That would be your H, and what's the length of the coupler. Using this very simple equation, you can find what is the reduction or percentage of reduction of displacement ductility capacity. So our splice column has a reduced displacement ductility capacity compared to unspliced cast-in-place column. Very simple, very easy. Whatever practice you have now for CIP, just follow that, and at the end, update your displacement ductility capacity for CIP for coupler. And then the second method, same ideology, same method, but we will update the plastic hinge length equation of AASHTO. So AASHTO has this one as the plastic hinge length. If you know where the coupler is, you know the length of the coupler, and if you know the rigidity of the coupler, you can reduce your plastic hinge length based on those information. So that would be your second method, and then you can do a pushover analysis or moment curvature analysis, just following AASHTO, and calculate your displacement ductility capacity, whatever you feel comfortable, or use it for practice. The last one is a pushover analysis. You know where your coupler is, you know your stress strain diagram of your coupler. You can model that. So assign those stress strain diagram to each fiber of the coupler or bar. For unspliced column, use your typical fiber section analysis and assign the conventional strain bar diagram to it. Then for concrete, you follow Manders or whatever you are using for confined, unconfined concrete, and perform a pushover analysis. For example, here I have a coupler shifted a bit, so there should be one element to take care of that region, the coupler region, element 2, the column above should be the third element. Then you do a typical pushover analysis for it. We wanted to evaluate all of these three methods. We tested 6 columns in this study. we compiled 4 other couplers from different study from Haber and Dr. Pantelidis in Utah, and one from NCHRP 935, and made a database of 10 columns that you can you have all information, and you can check your 3 design method for it. So let's do that. For the first one, which is simply updating your ductility, we went through the database and we found that this design equation is simple, overall conservative, and valid only for seismic couplers. For example, if you remember, PHT was non-seismic coupler. If you want to use this guy, you are wrong by almost 50%, because this equation has not been calibrated for non-seismic couplers. Only it can take care of seismic couplers. So that was a good thing to have. It was a mistake for unknown reason, but that was a good mistake to make, and check all of these equations, see if they are valid. So again, very simple equation, valid. Typical beta value for design is 0.5 to 1, and we see that most of or for most columns, we are within a reasonable accuracy and level of conservatism. So it's good to go. The second model or method is more involved. You need to do a kind of pushover analysis, but it is more accurate than the first one, and it's overall conservative, and it's only again valid for seismic couplers. Again, if you do it for non-seismic ones, you are off. And the last method, which is a let me go over how I did, or how I calculated these points in this chart. You know the column properties. You can do a moment curvature analysis, for example, and obtain all the requirements of the AASHTO SDS. And then you know your coupler location, length, and beta. You can update your plastic hinge length equation and put back in your pushover analysis or moment curvature, and find your updated displacement capacity or displacement ductility capacity, whatever you're basically comfortable. Here's one example, 4% error. For the other one, we had from 0 error to 15% or 16% error. So overall, very accurate method. But the most accurate method and the most involved method is a pushover analysis. I'm showing for 6 columns that we tested here. The black one is the calculated, and the red one is the measured test data. Overall, it can capture all the column behaviors. Even the one with non-seismic coupler, we were able to find the failure point of the column exactly as it was in the test. But again, it's more involved, need more time and more resources to perform those. But it's valid for any kind of coupler. So overall, all 3 methods that we have right now are valid with 10 columns within database, and we should be able to use those confidently for design purpose. So as a kind of quick summary and conclusion of the study, we have found that overall 3 parameters affect the coupler and column behavior. That's the coupler length, coupler location, and the rigidity of it. And when you put those couplers that can have a consistent fracture of the bar as the failure mode, you will see a reduction in displacement capacity from 3% to 45% when they are using columns. And the force or lateral strength will be changed, but no more than 15% in a precast column with couplers. And overall, all 3 methods that we currently have should be viable. And all columns that we tested met all requirements of AASHTO. We would be feeling more comfortable if one of those with non-seismic coupler change the performance and make it seismic coupler, then all of those should be okay to use in any state of the nation. And the database that we just discussed is out there. Feel free to use data for your validation or any further study that you have. And with that, I will say that all of these data is available in my website, or you can go also to MPC and download the 2 reports that we have there. All of these information and validations are within our MPC publications. So with that, I will open the floor for any question that you might have.
I was very happy to hear that you're working with Dr. Panelides out in Utah. He's been doing quite a few presentations on this, some of these same concepts as well. So it's really good to hear that. So thank you for sharing that.
Sure.
He has a presentation coming up, I believe, in August, actually.
Nice.
So on one of his new topics as well.
Perfect.
All right, I'm not seeing any questions come in. So with that, I would just like to thank you for sharing your research and what you found, and it's very extensive, so very informative and certainly appreciated by those who are in attendance today, and as well as our partner states who will take away some valuable information from this. So thank you for that. Everyone else, thank you for attending today's TLN event. We appreciate your time, participation, and attention, and I do sincerely hope that you enjoyed and gained some new knowledge from today's session. I would encourage you to visit our website at translearning.org for upcoming learning opportunities and to access our learning management system. If you do see a topic out there that is of interest, please do share that with your peers so that they have the opportunity to sit in on this fantastic training as well. With that being said, thank you everyone again for your time and attention. Have a wonderful rest of your week, and don't forget to be awesome. Have a great week.